March 23, 1944. 28,000 feet over Brunswick, Germany. Captain Robert Johnson pressed his throttle to the firewall and waited for the surge of power that should have come. His P-51 Mustang, serial number 43-6742, carried the name Ridge Runner, painted in white letters across the cowling. The engine note changed, deepened, but something was wrong. The response wasn't crisp. It wasn't immediate. It felt sluggish, hesitant, like the Packard Merlin under his nose was thinking about the request before delivering. 2,000 yards ahead, a Focke-Wulf 190 was pulling away. Not dramatically, not the way a superior aircraft outclasses an inferior one, but steadily, incrementally, the gap widening by 10 yards, then 20, then 50. Johnson's airspeed indicator showed 385 miles per hour at altitude. The manual said his Mustang should do 440. The gap between what his aircraft was supposed to deliver and what it actually produced might as well have been an ocean. Through his headset, Johnson heard Lieutenant Miller's voice, strained and urgent. "Ridge Runner, this is Buckeye 3. My boost pressure's off. I'm showing 18 pounds, should be reading 25. Johnson glanced at his own manifold pressure gauge. Same problem. 18 pounds per square inch when the Packard Merlin V1650-7 was rated for 25 at war emergency power. The math was brutal and simple. 7 pounds of missing boost pressure translated to roughly 200 horsepower, 200 horses that weren't showing up when American pilots needed them most. The Focke-Wulf pilot, probably a veteran with the Jaguar band, knew exactly what he was doing. He wasn't trying to dogfight. He was simply flying straight and level at maximum sustained cruise, betting that the American fighter pursuing him couldn't maintain the pace. He was right. Johnson watched the German aircraft shrink to a speck, then disappear entirely against the winter sky. His Mustang, the fighter that intelligence briefings called the best escort in the war, the aircraft that should have caught that 190 with power to spare, had just been outrun in level flight. Back at Debden Airfield in England, Johnson climbed down from his cockpit and walked directly to the crew chief's station. Staff Sergeant Frank Kowalski was already waiting, wrench in hand, the expression on his face suggesting he'd heard this complaint before. "The boost pressure's off again, Frank. We're 7 pounds light across the board. I watched a 190 just fly away from us." Kowalski nodded slowly, pulling out a maintenance log that was getting thick with similar entries. "Third time this week, sir. I've checked the supercharger, the intercooler, the fuel mixture. Everything tests within spec when we run it on the ground, but in combat, at altitude, the power just isn't there." Johnson looked at the Packard Merlin V1650-7, the engine that was supposed to be identical to the legendary Rolls-Royce Merlin 61 that powered the British Spitfire 9. Same specifications, same blueprints, same theoretical output. Two-stage, two-speed supercharger, liquid-cooled V12, producing 1,590 horsepower at 21,000 feet. On paper, the engines were twins. In reality, they were cousins at best, strangers at worst. What nobody had explained to Johnson, what the procurement officers and production managers hadn't advertised, was that copying a British engine was not the same as replicating British manufacturing. The Rolls-Royce Merlin was the product of decades of refinement built by craftsmen in Derby, England, who understood that precision wasn't just a specification, it was a philosophy. The Packard Motor Car Company of Detroit, Michigan, had received the license to build Merlins in 1940. They'd received the blueprints, the specifications, the engineering drawings. What they hadn't received, what couldn't be transmitted through documentation, was the accumulated knowledge of how to actually make it work. The story of why the Packard Merlin never quite matched its British parent begins not in America, but in the green fields of southern England, in the mind of a man who understood that engine design was equal parts science and art. His name was Ernest Hives, and he was about to teach the Americans a lesson in manufacturing they'd spend the entire war trying to learn. Before the Merlin transformed the Mustang into a legend, the P-51 was a remarkable failure. When North American Aviation designed the aircraft in 1940, they'd created an aerodynamic masterpiece, a fighter with the lowest drag coefficient of any aircraft in its class. The laminar flow wing was revolutionary, the fuselage sleek and efficient. But North American had made a critical mistake. They'd fitted it with an Allison V1710 engine, a power plant that was excellent at low altitude, but gasped for air above 15,000 feet. The Allison lacked an efficient supercharger, the mechanical compressor that forced air into the cylinders at high altitude where atmospheric pressure dropped. Without it, the P-51 was fast down low, but useless as an escort fighter. Bombers flew at 25,000 feet. The Allison-powered Mustang couldn't maintain speed or maneuverability up there. It was like building a race car with a lawnmower engine. The British, receiving the first Mustangs through Lend-Lease in 1941, immediately recognized the problem. They also recognized the solution. Rolls-Royce test pilot Ronald Harker flew a Mustang 1 at Boscombe Down and filed a report that changed aviation history. This airframe is exceptional, fitted with a Merlin 61, and it will outperform anything in the sky. The Merlin 61 was the latest evolution of Rolls-Royce's masterpiece, a two-stage, two-speed supercharged engine that maintained power output all the way to 30,000 feet. When British engineers shoehorned a Merlin 61 into a Mustang airframe in October 1942, the result was staggering. The aircraft that had been mediocre became magnificent. Top speed jumped from 390 miles per hour to 441. Service ceiling increased from 30,000 feet to 41,900. Range, already impressive, extended even further. The Americans took notice immediately. North American Aviation and the U.S. Army Air Forces recognized they'd found their perfect escort fighter. But there was a problem. Rolls-Royce couldn't produce enough Merlins to supply both British and American aircraft. The solution seemed obvious. Packard Motor Car Company would build Merlins under license in Detroit. The blueprints would be transferred, the specifications replicated, and American mass production efficiency would deliver engines in quantities Rolls-Royce couldn't match. It sounded perfect. It was a disaster. The first Packard-built Merlin E5 1650-3 rolled off the assembly line in August 1941. It was dimensionally identical to the Rolls-Royce original. The bore and stroke matched. The displacement was correct. The compression ratio duplicated. On paper, it was the same engine. On a dynamometer test stand, running under controlled conditions, it produced nearly identical power figures. But when pilots flew Packard Merlin-powered aircraft in combat at altitude under sustained maximum load, they noticed something. The engines weren't quite right. Power delivery was inconsistent. Some engines produced full rated output. Others fell short by 5, 10, sometimes 15%. Boost pressure fluctuated. Operating temperatures ran higher. Component failures occurred more frequently. The problem wasn't that Packard built bad engines. They built good engines. They just couldn't build Rolls-Royce engines, not really, because the secret of the Merlin wasn't in the blueprints. It was in the manufacturing. Rolls-Royce's Derby factory operated on principles that seemed almost medieval to American mass production experts. Tolerances were held to levels that U.S. manufacturers considered unnecessary. Components were hand-fitted. Bearing surfaces were hand-scraped. Supercharger impellers were individually balanced. Quality control inspectors rejected parts that met specifications but didn't meet standards, a distinction that made no sense in American terminology. Ernest Hives, Rolls-Royce's managing director, understood something fundamental. An engine was not just an assembly of parts. It was a system where microscopic variations in one component affected the performance of every other component. The gap between a piston and cylinder wall measured in thousandths of an inch determined oil consumption, blow-by, and power output. The balance of a crankshaft, adjusted to within grams, affected vibration and bearing life. The clearance in a supercharger housing, held to tolerances most manufacturers considered impossible, determined boost pressure efficiency. Packard received blueprints that specified tolerances. What they didn't receive was the culture that treated those tolerances as minimum standards rather than targets. In Detroit, if a part measured within specification, it was acceptable. In Derby, if a part measured at the loose end of specification, it was suspect. The difference seemed trivial. The consequences were profound. The supercharger was where the differences manifested most dramatically. The Merlin's two-stage supercharger was a marvel of engineering. 2 compressor stages driven through a complex gear train with an intercooler between stages to reduce air temperature. The impellers spun at over 20,000 revolutions per minute, the tips moving at near supersonic speeds. At those velocities, microscopic variations in clearance, balance, or surface finish created enormous performance differences. Rolls-Royce supercharger impellers were cast, then machined, then hand-finished, then individually balanced to within 0.01 ounces. Each impeller was tested, adjusted, retested. The process took hours per unit. Packard attempted to replicate this, but faced immediate challenges. American foundries couldn't consistently produce castings with the fine-grained structure Rolls-Royce achieved. Machining tolerances, while impressive by U.S. standards, were looser than British practice. Hand finishing was limited because skilled craftsmen capable of the work were scarce. The result was superchargers that worked but didn't work quite right. Under laboratory conditions, on a test stand running at steady state, they produced acceptable boost pressure. In combat, at altitude, with temperatures fluctuating and loads varying, they lost efficiency. A Rolls-Royce supercharger might deliver 95% efficiency under operational conditions. A Packard supercharger might deliver 88%. 7% doesn't sound like much. 7% of boost pressure at 25,000 feet was the difference between catching an enemy fighter and watching it escape. Bearing quality was another divergence point. Rolls-Royce used a specialized bearing material, a lead bronze alloy with specific grain structure and hardness. They sourced it from British metallurgical suppliers who'd spent decades perfecting the formula. Packard attempted to use American equivalents, alloys that met specifications but had subtly different properties. The bearings wore faster, required more frequent replacement, and under extreme loads, failed more often. The Americans tried to solve these problems through brute force. Packard invested millions in new machinery, hired consultants, sent engineers to Derby to observe. Rolls-Royce, for their part, was remarkably cooperative, sharing knowledge that would normally be proprietary. But some things couldn't be transferred. The British had a foreman at Derby named Albert, who'd worked on Merlin production since 1936. He could hear an engine running and tell you if the supercharger clearance was off by 0.02 of an inch. Not through instrumentation, through sound. He'd listened to thousands of Merlins, knew what right sounded like, what wrong sounded like. That knowledge wasn't in any manual. There was a quality control inspector named Margaret who rejected cylinder blocks that passed all dimensional checks because the surface finish looked wrong to her eye. She was right every time. X-ray inspection later proved the blocks she rejected had internal flaws not visible to measurement. Her ability to see what instruments couldn't detect saved countless engines from failure. You couldn't train someone to do that. It came from years of experience and an intuitive understanding of metal. Rolls-Royce had dozens of people like Albert and Margaret. Packard had production workers following procedures, doing their jobs competently, but without the accumulated wisdom that turned manufacturing from process to craft. If you want to see where these stories are going and make sure you catch every detail, hit that subscribe button now and turn on notifications. These hidden histories don't tell themselves, and your support helps us keep digging into the stories the textbooks missed. By mid-1943, the performance gap between British and American-built Merlins was undeniable. RAF Spitfire 9s, powered by Rolls-Royce Merlin 61s, consistently outperformed P-51B models with Packard V 1650-7s at altitude. The difference wasn't dramatic enough to make the Mustang ineffective, but it was significant enough that pilots noticed. Captain Don Gentile, one of the highest-scoring American aces in Europe, flew both British and American Mustangs. His observations were recorded in debriefing reports that the Army Air Forces tried to keep quiet. "The Packard Merlin is good," he said, "but the Rolls is better. You can feel it in the throttle response. The British engine accelerates faster, holds boost pressure more consistently, runs smoother under sustained high power. It's not night and day, but in combat, those margins matter." Squadron engineering officers started keeping informal logs comparing engine performance. At Debden, at Leiston, at Bodney, the pattern was consistent. Packard Merlins required more frequent maintenance, experienced more oil consumption, showed higher operating temperatures, and delivered slightly less power than rated specifications suggested. The engines weren't failing catastrophically. They were simply underperforming incrementally, a death by 1,000 small deficiencies. The problem extended beyond just the Mustang. The P-40F Warhawk used Packard Merlins. The Lancaster bombers built in Canada used Packard Merlins. Every aircraft powered by American-built engines faced the same subtle performance deficit compared to British originals. Packard's engineers were frustrated. They'd followed the specifications. They'd invested in tooling. They'd implemented quality control procedures that were, by American standards, exceptional. Yet they couldn't close the gap. The issue went deeper than anyone wanted to admit. It was cultural. American manufacturing philosophy, perfected by Henry Ford and his disciples, emphasized interchangeability and efficiency. Parts should be machined to specification and assemble without fitting. Workers should follow procedures, not exercise judgment. Output should be maximized, costs minimized. This philosophy had made America the world's leading industrial power. It was perfect for producing automobiles, appliances, and consumer goods, but it wasn't perfect for producing Merlin engines. British manufacturing philosophy, inherited from centuries of craftsmanship tradition, emphasized getting it right over getting it done. A Rolls-Royce manager once explained the difference to an American observer. You build to tolerance. We build to standard. Tolerance is the acceptable range. Standard is the goal. Every component should be as close to ideal as human skill can achieve, regardless of whether it's within the acceptable range. This fundamental philosophical difference manifested in 1,000 small ways. When a Packard machinist finished boring a cylinder, he measured it, confirmed it was within tolerance, and moved on. When a Rolls-Royce machinist finished the same operation, he measured it, examined the surface finish, checked for microscopic tool marks, sometimes rejected work that passed specification because it didn't meet his personal standard. The American approach was more efficient. The British approach produced better engines. There was no villain in this story. Packard wasn't incompetent. Rolls-Royce wasn't hoarding secrets. The gap was simply the accumulated result of different manufacturing philosophies applied to an engine that demanded perfection in ways specifications couldn't capture. But that gap had consequences. In the skies over Europe, where American pilots faced Luftwaffe fighters that were often technically superior, every advantage mattered. A P-51 that should have caught a Focke-Wulf 190 but didn't, because the Packard Merlin delivered 92% of rated power instead of 100%, wasn't just frustrating, it was potentially deadly. By late 1943, field modifications began appearing, the unofficial network of solutions that always emerges when official channels fail to solve problems. At Debden, a crew chief named Eddie Condon started experimenting with supercharger boost pressure adjustments, methods remarkably similar to what Sergeant Banks was doing with Mosquito Merlins. By carefully selecting engines that showed strong performance characteristics and advancing their boost pressure settings slightly beyond Packard's specifications, Condon found he could extract performance closer to what the Rolls-Royce originals delivered. The modifications carried risks. Higher boost pressure meant higher cylinder temperatures, increased stress on bearings and connecting rods, reduced engine life. But Condon's logic was the same as Banks's had been. An engine that lasted 130 hours instead of 150 was acceptable if it kept a pilot alive today. His approach spread through informal channels. Crew chiefs talked to each other, shared techniques, compared results. By early 1944, modified Packard Merlins were appearing across 8th Air Force fighter groups. The modifications weren't documented in maintenance logs with honest descriptions. They were buried under vague entries like boost control optimization or fuel mixture calibration. Packard's field service representatives noticed engines returning for overhaul with wear patterns inconsistent with standard operation. They knew what was happening. The company faced an uncomfortable choice: officially object and force the modifications to stop, or quietly allow the practice to continue because it improved combat performance. They chose silence. The engineering team at Packard's Detroit plant began studying failed engines more carefully, looking for patterns. What they discovered was enlightening and depressing. The engines that performed best, that came closest to matching Rolls-Royce output, were those built during specific production runs when certain skilled workers were on shift, when particular batches of raw materials were used, when quality control procedures were enforced most rigorously. In other words, the best Packard Merlins were the ones that most closely approximated British manufacturing practice, even accidentally. The company attempted to systematize these successes, to capture what worked and implement it across all production. But you couldn't systematize Albert's ability to hear a misadjusted supercharger or Margaret's eye for flawed castings. What Packard could do, and did do very well, was produce engines in extraordinary quantities. By 1944, the Detroit plant was delivering over 1,000 Merlin engines per month. Rolls-Royce's Derby facility, even running at maximum capacity, couldn't approach that output. The American engines might have been 90 to 95% as good as British originals, but there were 3 times as many of them. This became the strategic calculus: quality versus quantity. The age-old military trade-off resolved in favor of numbers. Better to have 3 P-51s with good engines than 1 Spitfire with a perfect engine. Better to lose some performance efficiency than lose the air war for lack of aircraft. The pilots who flew these aircraft understood the compromise they'd inherited. They adapted. They learned their engine's quirks, the specific power settings that delivered best performance, the altitudes where their particular Packard Merlin ran strongest. They communicated with crew chiefs, building relationships where information flowed both ways. They survived. But they also wondered, what if? What if the Packard Merlin had matched the Rolls-Royce original exactly? How many pilots would have caught that enemy fighter that got away? How many would have made it home who didn't? The performance gap was never officially acknowledged. Army Air Force's reports emphasized the P-51's success, its impressive kill ratio, its effectiveness as an escort fighter, all true. But the reports didn't mention that British Mustang squadrons, flying the same airframe with Rolls-Royce engines, consistently showed slightly better performance statistics. The divergence was subtle enough that most people missed it. But the engineers knew. The pilots knew. And in the quiet moments between missions, in conversations that weren't recorded in official logs, the truth was discussed. "We're flying good aircraft," one pilot told his wingman, "but the Brits are flying great ones, and the only difference is the engine." In Derby, Ernest Hives received reports from liaison officers about Packard Merlin performance in combat. He never criticized publicly. Rolls-Royce needed Packard's production capacity. The alliance was strategic necessary, but privately, to his senior engineers, he expressed a kind of sad vindication. They thought they could copy excellence, he said. But excellence isn't copied. It's earned. It takes time. It takes skill. It takes a commitment to standards that can't be written in specifications. The Americans will learn this eventually. The question is whether they'll learn it in time. The lessons were already being learned in the hardest possible classroom. Over Germany, over France, in the vast aerial battles that decided the war in Europe, American pilots were discovering that engineering on paper and engineering in practice were different things. The Packard Merlin worked. It powered thousands of aircraft to victory, but it was always a compromise, a translation that lost something essential between languages. The real tragedy wasn't that the Packard Merlin underperformed. The tragedy was that American manufacturing excellence, legitimate and world-changing in its own right, had been asked to replicate something it wasn't designed to replicate. Packard was magnificent at mass production. Rolls-Royce was magnificent at precision craft production. These were different excellences, both valuable, both necessary. But when you needed an engine to operate at the ragged edge of performance, at altitudes where every horsepower mattered, in temperatures that stressed materials to their limits, you needed Rolls-Royce excellence. And that was something Packard, despite its best efforts, couldn't deliver. The summer of 1944 brought the campaign that would finally expose the full dimensions of the Merlin Gap. Operation Overlord, the invasion of Normandy, demanded air superiority so complete that Allied ground forces could advance without fear of Luftwaffe attack. P-51 Mustangs would provide long-range escort for bomber streams, patrol over the beachhead, intercept German fighters before they reached the invasion fleet. It was the mission the Mustang had been designed for. It was also the mission where every percentage point of engine performance mattered. On June 4th, 2 days before D-Day, the weather over the English Channel was terrible. Low clouds, high winds, rain squalls that reduced visibility to hundreds of yards. General Eisenhower postponed the invasion by 24 hours. But the air campaign continued. Fighter sweeps penetrated deep into France, attempting to draw out the Luftwaffe to attrit German fighter strength before the landings. Captain Robert Johnson, the same pilot who'd watched a Focke-Wulf escape 3 months earlier, flew his fourth mission of the day at 1700 hours. His Mustang, still carrying the name Ridge Runner, had received engine maintenance the night before. The crew chief, Sergeant Kowalski, had implemented one of Eddie Condon's modified boost pressure settings, advancing the limit from 18 pounds to 21 pounds per square inch. It's not Rolls-Royce power, Kowalski had said, but it's closer. The mission profile called for a fighter sweep over Normandy at 24,000 feet, hunting German interceptors, before they could organize against the massive bomber stream scheduled for dawn. Johnson's flight of 4 Mustangs crossed the French coast at Cherbourg and turned southeast toward Caen. They found the enemy 12 minutes later, 6 Messerschmitt 109 G variants, climbing hard from an airfield near Falaise. The German formation was led by an experienced pilot, probably a Staffelkapitän with multiple kills. He recognized the Americans immediately and made the smart, tactical choice. Don't dogfight, don't engage low and slow. Climb to altitude, use the 109's excellent high-altitude performance, force the Americans to chase you into thin air, where engine power matters most. Johnson pushed his throttle forward and activated the boost override that Kowalski had modified. The Packard Merlin responded, manifold pressure climbing to 21 pounds, the engine note hardening into that distinctive howl that Merlin pilots learned to love. But even with the modification, even with every ounce of power the American engine could deliver, Johnson felt the performance gap. The 109 was pulling away, not quickly. The Messerschmitt couldn't outrun a Mustang in level flight, but in a sustained climb to altitude, The German fighter's Daimler-Benz engine gave it an edge. The DB605A could maintain power output to nearly 30,000 feet. The Packard Merlin Viv 1650-7, even modified, started losing efficiency above 26,000. Johnson watched his airspeed bleed off as both aircraft clawed for altitude. At 28,000 feet, the gap had widened to 800 yards, too far for effective gunnery. The German pilot knew exactly what he was doing, climbing into thin air where his engine's supercharger gave him advantage. Then something unexpected happened. A second flight of Mustangs appeared, diving from 30,000 feet, cutting off the German formation's escape route. These weren't American aircraft. Johnson recognized the markings immediately. RAF Squadron 336, flying Mustang 3s with Rolls-Royce Merlin, 68 engines built in Derby. The difference was visible instantly. The British Mustangs, operating at the same altitude, maintained speed and acceleration that Johnson's Packard-powered aircraft couldn't match. Where Johnson was struggling to close distance, the RAF pilots closed effortlessly. The lead Spitfire, that's what the British pilots still called their Mustangs, despite the technical redesignation, positioned behind the Staffelkapitan's 109 at 600 yards and opened fire. The German aircraft disintegrated. 20-millimeter cannon rounds, the British Mustangs carried different armament than American variants, shredded the Messerschmitt's wing. The pilot bailed out at 29,000 feet, parachute deploying in the thin air. Johnson watched the engagement with professional appreciation and personal frustration. The RAF pilot had made it look easy. The Rolls-Royce engine had delivered power at altitude that let him maneuver, accelerate, and engage with confidence. Johnson's Packard Merlin, even modified, had left him chasing shadows. After the mission, back at Debden, Johnson found the RAF squadron commander in the officers' mess. Squadron leader David Henderson was drinking tea and reviewing combat film with his intelligence officer. Johnson introduced himself and asked the question that had been burning since the engagement. "Your Mustangs, they're faster than ours at altitude. Same airframe, same specifications, but you had power, we don't. What's different?" Henderson looked at him with the kind of polite British restraint that somehow made statements more cutting. "The engines, old boy. We're running Rolls-Royce Merlins from Derby. You chaps have the Packard versions. Dimensionally identical, theoretically equivalent, practically superior in our case. It's not a criticism of American manufacturing. It's simply a fact. Rolls-Royce has been building these engines since 1933. They've learned things that can't be put in blueprints." Johnson nodded slowly. "I thought it was just me. Thought maybe I was flying wrong, or my crew chief wasn't maintaining properly. But it's the engine. We're flying good aircraft with 90% engines." Henderson sipped his tea. 90% of excellent is still very good. And you Americans have 3 times as many of them. That counts for something. Numbers have a quality all their own, as someone once said. But yes, if you want the absolute best performance, Rolls-Royce is what you need. We're rather proud of that. The conversation spread through the fighter groups. Pilots compared notes, shared experiences, confirmed what many had suspected. The Packard Merlin was good, but not quite good enough. For most missions, the difference didn't matter. The Mustang's range, speed, and firepower made it effective regardless. But in edge cases, in the fights where performance margins determined survival, the gap was real. 8th Air Force Headquarters received reports about the performance disparity. The response was predictable. Maintain operational security. Don't discuss engine performance differences in ways that might undermine pilot confidence. Emphasize the P-51's overall success rate. Focus on training, tactics, and numerical superiority. In other words, acknowledge the problem privately, but ignore it publicly. But ignoring a problem doesn't make it disappear. Through summer and fall of 1944, as Allied fighter operations intensified, the Merlin gap continued to manifest. Some Mustang squadrons reported kill ratios slightly lower than expected. Engine failures occurred more frequently than projections suggested. Operating costs, measured in maintenance hours per flight hour, ran higher than British units with identical aircraft. The United States Army Air Forces commissioned a quiet study. Compare RAF Mustang performance with USAAF Mustang performance, control for pilot experience, and mission profiles. Isolate the variables. The study concluded what pilots already knew. British Mustangs, powered by Rolls-Royce engines, showed 5 to 7% better performance across multiple metrics: climb rate, sustained speed at altitude, throttle response, engine reliability. 5 to 7% doesn't sound significant. In aerial combat, it's the difference between winning and dying. The study was classified and filed away. Before we get to the final part of this story, the part where wartime necessity forced solutions that peacetime engineering couldn't solve, make sure you're subscribed to this channel. Hit that bell icon so you don't miss the conclusion, and drop a comment telling me which aspect of this story surprised you most. Your engagement helps these forgotten histories reach more people. Packard Motor Car Company knew it had a reputation problem. By late 1944, word had spread beyond military channels. Aviation journalists, always looking for stories, had heard rumors about Merlin performance differences. Packard's competitors, particularly Wright Aeronautical and Pratt & Whitney, were happy to quietly suggest that maybe Detroit wasn't quite ready for precision aero engine manufacturing. The company responded with what it did best: production capacity. If Packard couldn't build engines as good as Rolls-Royce, it would build so many engines that quality differences became irrelevant through sheer volume. Monthly production increased from 1,000 units to 1,400. Costs dropped through efficiency improvements. Delivery times shortened. From a strategic perspective, this was exactly right. The Allied air campaign needed engines in quantity. Better to have adequate engines in abundance than perfect engines in scarcity. But from a pilot's perspective, sitting in a cockpit at 28,000 feet watching an enemy fighter pull away because your engine couldn't deliver rated power, strategy was cold comfort. The field modifications that crew chiefs like Eddie Condon had pioneered became increasingly sophisticated through late 1944 and into 1945. The unofficial network of engine tweaking expanded beyond simple boost pressure adjustments. Mechanics experimented with fuel mixture ratios, supercharger impeller timing, ignition advance curves. They shared techniques through informal channels, creating a distributed research and development program that Packard's engineering department didn't officially acknowledge but quietly monitored. Some modifications worked brilliantly. A crew chief at Bodney discovered that advancing ignition timing by 2 degrees at high altitude settings improved power delivery by 3 to 4%, enough to close part of the gap with Rolls-Royce performance. The technique spread across multiple fighter groups within weeks. Other modifications failed catastrophically. A well-intentioned attempt to increase boost pressure beyond sustainable limits resulted in 3 engine failures in 1 week, including one that destroyed a Mustang on takeoff. The pilot survived, but the aircraft was written off. The failures prompted more careful experimentation, better documentation, systematic testing, rather than trial and error. By early 1945, the cumulative effect of thousands of small improvements by hundreds of skilled mechanics had narrowed the performance gap between Packard and Rolls-Royce Merlins from 7% to perhaps 3 or 4%. Still measurable, still significant to pilots who needed every advantage, but reduced from crisis level to manageable difference. Packard's engineering team, studying the field modifications, incorporated successful techniques into production standards. The V1650-9 variant, introduced in early 1945, included several changes derived from crew chief innovations. Boost pressure ratings increased slightly. Fuel mixture calibrations were optimized for high-altitude operation. Quality control procedures were tightened, with special attention to supercharger balance and bearing clearances. The Dash 9 was the closest Packard ever came to matching Rolls-Royce performance. In testing, it showed only 2% power deficit compared to British-built Merlins. In operational service, pilots reported much improved performance. The gap hadn't disappeared, but it had narrowed to the point where pilot skill and tactical situation mattered more than engine pedigree. But by the time the V-1650-9 reached squadrons in quantity, the war in Europe was ending. The Luftwaffe, starved of fuel and pilots, posed minimal threat. The performance difference between good and excellent engines no longer determined survival. The final chapter of the Merlin story belongs not to America or Britain, but to the aircraft that proved the engine's ultimate capability. The de Havilland Hornet, designed in 1943, was a long-range fighter that pushed Merlin performance to absolute limits. It used two Rolls-Royce Merlin 130 engines, refined versions of the 60 series with improved supercharging and higher boost pressure ratings. The Hornet could reach 475 miles per hour at 22,000 feet, making it the fastest piston engine aircraft the RAF ever operated. It could maintain that speed for hours, cruising at power settings that would have destroyed earlier Merlin variants. The engine's reliability, even under sustained maximum load, was legendary. Packard never attempted to replicate the Merlin 130. By 1945, the company had moved on to jet engine development. The era of piston fighters was ending. The lessons learned from 5 years of chasing Rolls-Royce performance would be applied to new technologies, new challenges. But those lessons were profound. American manufacturers learned that precision matters in ways specifications can't capture, that tolerances are minimums, not targets. That accumulated expertise, the kind that comes from decades of refinement, can't be replicated through documentation. That some manufacturing problems can't be solved by throwing money and resources at them. That excellence is earned through sustained commitment to standards that seem excessive until they prove essential. Rolls-Royce learned complementary lessons, that even with superior quality, you need sufficient quantity to matter strategically. That American mass production techniques, while sacrificing some precision, enabled output impossible through traditional craft methods. That collaboration with Packard, despite the frustrations, ultimately produced more engines than Rolls-Royce alone could have delivered. Both companies emerged from the war as leaders in aero engine manufacturing. Their approaches, once seen as incompatible, would increasingly blend. Post-war jet engines combined American production efficiency with British precision engineering. The divide narrowed. For the pilots who flew P-51 Mustangs with Packard Merlins, the legacy was more personal. They'd flown good aircraft, not perfect aircraft. They'd adapted to engines that required understanding rather than just operation. They'd survived through skill, tactics, and the efforts of crew chiefs who worked miracles with inadequate tools. Robert Johnson finished the war with 27 confirmed kills, making him one of the top American aces. He never flew a Rolls-Royce-powered Mustang. His Ridge Runner, with its modified Packard Merlin and Sergeant Kowalski's careful maintenance, brought him home from every mission. That was enough. In his post-war memoir, Johnson wrote about the engine question with characteristic honesty. We always knew the British had slightly better engines. It was one of those things everyone understood, but nobody talked about officially. Did it matter? Sometimes. There were fights I might have won more easily, enemies I might have caught, if I'd had those extra few miles per hour. But I also flew with confidence because I had the best crew chief in the Air Force and an aircraft that, while not perfect, was good enough to keep me alive. That's all any pilot can ask. Eddie Condon, the crew chief who pioneered field modifications at Debden, was offered a job at Packard after the war. He turned it down, choosing instead to open a small aircraft maintenance shop in California. When asked about his wartime work, he was philosophical. We did what we had to do with what we had. Could the engines have been better? Sure. But they were good enough, and we made them better. Sometimes that's all you can do. The Packard Motor Car Company produced 55,000 V1650 series Merlin engines between 1941 and 1945. They powered P-51 Mustangs, Canadian Lancaster bombers, and various other aircraft. The engines were reliable, effective, and produced in quantities that helped win the war. They were 90 to 95% as good as Rolls-Royce originals. In most contexts, 95% is excellent. In precision engineering, it's the gap between good and great. In aerial combat, it's the difference between catching an enemy and watching him escape. In manufacturing philosophy, it's the space between hitting specifications and achieving standards. The story of the Packard Merlin isn't a story of failure. It's a story of limits. The limits of what can be replicated through documentation. The limits of mass production efficiency when applied to precision craft. The limits of American manufacturing philosophy when confronted with British engineering culture. Most importantly, it's a story about what pilots and mechanics learned, that excellence can't be copied, only earned, that some gaps can't be closed through effort alone. That good enough is sometimes all you get, and you make it work. Rolls-Royce continued building Merlin engines until 1950. The final version, the Merlin 135, produced over 2,000 horsepower and powered some of the last piston fighters before jets made them obsolete. Total Rolls-Royce production reached 160,000 engines, a testament to British manufacturing sustained through 6 years of war and beyond. The company's reputation for precision, for holding standards that seemed excessive, for building engines that performed beyond specifications, became legendary. It was a reputation earned through exactly the kind of manufacturing philosophy that Packard couldn't replicate. Commitment to excellence that couldn't be written in blueprints. In the decades since, aviation historians have debated the Merlin gap. Some argue it's been exaggerated, that performance differences were minimal and operationally insignificant. Others point to the evidence, pilot testimony, maintenance records, comparative testing data, and argue the gap was real and mattered. The truth, as usual, is nuanced. The Packard Merlin was a good engine that powered effective aircraft to victory. It was also slightly inferior to the Rolls-Royce original in ways that mattered to pilots who flew at the edge of performance. Both statements are true. What's undeniable is the broader lesson about manufacturing and engineering. When you attempt to copy excellence, you discover that excellence isn't in the blueprints. It's in the accumulated knowledge, the practiced skill, the cultural commitment to standards that exist beyond specifications. Those things can't be transferred through documentation. They have to be learned slowly and painfully through years of refinement. American industry learned this lesson during World War II. The knowledge would be applied to post-war manufacturing, aerospace engineering, and countless other fields. The gap between Packard and Rolls-Royce Merlins was a tuition payment on an education that made American manufacturing more precise, more careful, more attentive to details that seemed excessive until they proved essential. And for the pilots who flew Mustangs with Packard engines, who adapted to their quirks and survived through skill and determination, the lesson was simpler. You fly the aircraft you have, not the aircraft you wish you had. You work with your crew chief. You learn your engine. You compensate for its limitations. You survive. Captain Robert Johnson, Squadron Leader David Henderson, Staff Sergeant Eddie Condon, they all understood this. They lived in the gap between ideal and real, between excellent and good enough. They made it work. That's the real story of why America's copied Spitfire engine couldn't quite match Britain's legendary design. Not because Americans couldn't build good engines, they could and did, But because excellence in precision engineering isn't copied, it's earned through decades of refinement, through accumulated knowledge that exists in the hands and eyes and ears of skilled workers, through cultural commitment to standards that can't be written down. Rolls-Royce had that. Packard didn't, not quite, not yet. The gap was real. The pilots knew it. The mechanics knew it. History recorded it. And in that gap, in that space between 95% and 100%, lies a lesson about manufacturing, engineering, and the limits of what can be replicated through will alone. Some things have to be earned. Some excellence can't be copied. The Merlin engine taught that lesson to a generation of American engineers. It was an expensive education, but like all good education, it changed how they understood their craft. And that, perhaps, was worth more than closing the gap.